let's look at flow as it gets close to the wall, where we start generating these frictional forces, and talk a little bit about boundary layer theory. You can take entire graduate classes and nothing of boundary layer theory, so we're going to touch the very brief, smallest bit. So what I want to do is let's look at flow over a knife-edged plate going at what we'll call a low Reynolds number, something on the order of 10. So we're going pretty slow. And so what happens is we start generating these viscous forces around the body. Now remember, we have this entire concept of no slip condition, so the fluid flow that is touching the wall will be going the same speed as the wall. Now in pipe flow, we have these boundary layers merging together to give us friction throughout the entire pipe, but this is unbounded flow. We do not have a pipe to contain it and to have the friction appear all around it. It's just going to be kind of in the fluid. And so much like being at the front of a ship and watching the waves and wake and everything churn up way in front of the ship, we're going to get the same thing with the flat plate, because we have little fluid element there that'll be 0, and he's connected to all of his friends, and so he'll be dragging them along. So he'll be retarding the motion of all these guys and slowing them down. Now eventually you get far enough away from the object that we don't have this frictional effect anymore. How do I know when I'm outside of this viscous region? Well, that's when the local velocity is going to be 99% of the free stream velocity. And so that's where we define the edge of this region. Now, because we have all this friction in this region, as you can see as we come in, we're going to get a displacement because things will start to slow down and it will cause a displacement of the streamlines that are coming in. So it's generating this bubble of friction all through this region. And so the thickness of this region is at a low rate is going to be roughly as long as the object is. So in this case, this is L, so this region will roughly be L. It's not an exact thing. Now, we define this as the boundary layer. And in fact, we use the Greek letter lowercase delta. We know we've talked about this before. Or can't let you go into the last set of lectures without continuing our classical Greek education. And we define lowercase delta as the boundary layer thickness. Now you'll notice that it grows as we move along the shape. And that's going to happen. As we get farther down the shape, it'll get bigger. So it's just the way it is. So what happens if we speed things up? So if I speed things up and go to a more high Reynolds number flow, and this is on the order of 10 to the 7, what's going to happen is much like when we look at our ship, if we go from the Kennedy to like a speedboat, we'll notice the wakes will change quite a bit. We'll notice that things get a lot smaller, it gets a lot tighter. It's kind of got this bullet shape to it. And the reason that it has this bullet shape to it is because we're going to have a laminar and a turbulent boundary layer around this object. But it's a much tighter region of viscosity around the fluid, where it's going to be viscous. And so that means that it's going to disturb the flow less. Remember, think about streamlined and blunt bodies too. Streamlined body is going to disturb the flow the least amount, which means it's going to have the smallest viscous region around it. And this is the inherent idea of boundary layers are a fascinating topic. It really comes down to why planes fly. We'll do very high-level stuff, but there's a lot coming on with this. And in fact, this was all first pointed out by a fluid scientist by the name of Prandtl. He was a German fluid scientist, I think around World War I era, maybe a little bit later, a little bit sooner, don't remember off the top of my head. Prandtl is important, and the reason that you know this guy is important is he has his own number. There is the Prandtl number, which we will not be dealing with in this class, but he is, needless to say, he's a huge deal, especially when we're talking about flight. Now, for boundary layer thicknesses, we have a couple of equations that we can use to approximate what the thickness is going to be. And I say approximate because this is a very difficult math equation. So we have some accepted formula for boundary layer thicknesses. And that's probably as deep as we're going to go in this class with boundary layers. And so the first will be for a laminar flow, because in fluids, everything comes down to either laminar or turbulent flow. And so laminar flow in flat plate theory is going to be talking about Reynolds numbers between 10 to the third and 10 to the sixth. And so that approximation is delta over x is equal to 5.0 divided by the Reynolds number based on x to the 1/2. It's all based on x means is along the plate. And then we have a turbulent flow. And so turbulent flow is going to be defined as any, I forgot to put my Reynolds number in here, so less than Reynolds number, less than 10 to the 6th. Turbulent flow will be a Reynolds number greater than 10 to the 6th. And the stated equation, or the used equation for that would be delta over x is equal to 0.16 divided by the Reynolds number based on x to the 1/7 power. And so as you can see, the larger the Reynolds number, the smaller the boundary layer would be. Not between laminar and turbulent, because it is going to grow as we go down here, but between a low flow state and a high flow state. And so this holds true for blunt bodies also, except there is an additional property. And so let's look at a sphere is our classical blunt body. And so in this case, we can see that the boundary layer is hugging the sphere very well. And it's beautiful. It's acting exactly like we'd hope it to. This is the ideal blunt body flow, though, because we don't get this perfectly behaved thin boundary layer and mythically thin wake as it comes off that. And that's what we call this, is the boundary layers and the frictional areas behind it is the wake, just like the wake on a ship. Blunt bodies do act like this, but we have another property, because what happens is as soon as we start to make this turn around the edge here, if the body is not sufficiently streamlined, the boundary layer basically cannot, quote unquote, hold onto the body anymore. The viscous effects become less important than the inertia effects. And so then what happens is the inertia causes the boundary layer to what we call separate from the body. And so in a blunt body, what we have is, so here we go, we've got this right here, the flow separation occurs, and you get all this churning in this wake behind the blunt body. Now, is this bad? Is this good? Well, it depends on what you're doing. In the case of like a golf ball, which we'll talk about later, it's actually not that bad because you have all this wake behind you. That's great because it reduces the amount of drag on the object. If you're in a plane, it's bad because you need the boundary layer to fly, and the wing will no longer be a lift-generating body if the boundary layer separates. We'll talk about both of those concepts in later lectures.